Hi, everyone. This is Dr. Li Tai, and welcome to Chapter 3 of Chemistry 101. In this chapter, we're going to discuss the structures of atoms, called atomic structure, and also we're going to discuss the periodic table. We have an overview of the periodic table, but the major part of this chapter, we're going to talk about how atoms are constructed, and especially more importantly, how electrons are arranged in our atoms. Okay, so first, again, this is the overview of this chapter. We're going to study the internal structure, some numbers, okay, the particles inside an atoms, their numbers, and we're going to look at the periodic table. And also in the second half of the chapter, like we said, we're going to talk about how electrons are arranged in or within atoms. Okay. Now, let's get started taking a look at the internal structure of an atom. Okay, internal structure of an atom. Like we seen last time in chapter 1, this is a picture of an atom, a helium atom, I think. If you look at the structure of the atom basically is a very small particle. The size of the atom is only around 100 picometer, or you can see it's 10 to the negative 10th meter of the size, tiny size. And you can see the atom is generally empty, but with a small, very tiny center. Okay, small, very tiny center. So what are these? What are the empty spaces? What are filled in the empty space? And also what is at the center of the atom is what we're talking about right now. Okay, first, this is a picture, okay, showing the structure of an atom. Of course, the previous one is a real electron microscope picture, but this one is like a mimic or cartoonized picture of an atom, showing you the empty space and also the center. As you can see that atoms are actually made of 3 subatomic particles. Okay, those subatomic particles are called electrons, protons, and neutrons. Okay, and specifically at the center of the atom, okay, we call the nucleus of the atom is actually made of 2 subatomic particles, the protons and the neutrons. So you can see that the nucleus at the center is composed of protons and neutrons. Of course, later on, we're going to see that protons are particles carry positive charges, but neutrons are particles that are neutral without charges. Okay, now you know that protons are positive charged. Okay, that means the whole nucleus is positively charged. Okay, the whole nucleus is positive charged. So we need something negatively charged to neutralize that positive charge to make the whole atom neutral. So that is where electrons are. Okay, are playing. What that is the function of the electrons. Electrons are actually filled in at the empty space of the atom outside the nucleus, the relatively larger empty space outside the nucleus. And electrons, of course, possess negative charges to neutralize the positive charge of the nucleus. Of course, again, the positive charge of the nucleus comes from the protons. So this is how an atom is constructed: a small, tiny nucleus, and also the empty space filled with electrons. Okay, this table shows you not only the charge, but also the masses of these particles and how the charge and mass are distributed in our atom is shown in this table. As you can see that for these 3 types of subatomic particles, only 2 particles comes with a charge. That is the proton. Each proton carries a positive 1 charge. Again, the charge is called relative charge. That's not the real amount of charge, but we assign the relative charge of +1 for a proton. And like we said, neutron in the nucleus does not have a charge, so neutron charge is 0. Then, in order for the whole atom to be neutral, we know that the electrons are negatively charged. Each electron carries a -1 charge. So you can see that proton and electrons, they carry opposite charge. One is +1, another one is -1. So that's why they can be neutral. And later on, we're going to talk about the numbers, how the numbers are relative to each other. So that is the charge: proton +1 charge, electron -1 charge, neutron 0 charge. Now, if you take a look at the mass, you will see that is also very interesting. The proton and neutron, their mass number is also proton and neutron. Their mass number is also close to each other, 1. Okay, we call that relative mass 1, but the real mass is here, actually shows 1.767 times 10 to negative 27 kilograms. That's the real mass, the actual mass in grams. But we call that actual mass a 1 mass unit. So the relative mass of a proton is very close to the relative mass of a neutron, which is 1 mass number. But if you take a look at the mass of the electron, okay, take a look at the mass of the electron, which is extremely small compared to the mass of the proton or the neutron. The mass of the proton or neutron, the mass number is 10 to negative 27. But the mass of the electron is 10 to negative 31, which is what? Like a 4 digits smaller. So compared to the mass of these two proton neutrons, the mass of the electron is so small that we assume the mass of the electrons is negligible. So we call the mass number of the electron 0. Or in this way, we assume what? We assume the mass of the atom is located at the nucleus, because we assume the mass of the electrons, technically they're not 0, but we assume the mass number is so small, they are negligible. So the mass number electron 0 compared to the mass number 1 for proton and neutrons. And that tells us, again, the mass of a nucleus, the mass of the atom is located in the nucleus, where proton and neutrons are located. So here again, this chart is very important, especially the relative mass and charge of these particles. Okay, the charge neutron is 0. So the charge of the proton and neutron electrons will kind of balance each other. And the mass, proton and neutron have similar mass of 1 unit, but the mass of the electron is negligible, so small compared to the mass of the other two types of particles. Okay, they're not 0, but technically they're not 0, but it's so small compared to the mass of these two other particles. So we assume the mass of the atom is concentrated at the nucleus. Okay, it's concentrated at the nucleus. So here, after we know these numbers, let's take a look how these numbers play the function of the atom. Okay, first, like we mentioned already, atoms are all neutral particles. So in order for an atom to be a neutral particle, carry no electric charge, we know the charge of the electron must balance charge of the proton. So in that sense, okay, because one is positive, one is negative. So in that sense, we have a conclusion here. For a neutral atom, the mass of the proton will always equal to the the number of protons will always equal to the number of electrons. Okay, the number must be equal because one is positive charge, one is negative charge. One proton is positive one electron is a negative one. So the number of proton and electrons must be equal in a neutral atom. This is a very useful and important conclusion. Okay, conclusion. Another one, okay, we want to know is the relative size comparison about the different parts of the nucleus. We know parts of the atom. We know the atom has a small nucleus at the center and also relatively empty space outside the nucleus filled with electrons. But you have an idea how small or how big, what's the relative size between the nucleus and the whole atom, or what's the size of the empty space. As you can see this picture, you may have a general idea. You can see the size of the atom is around 100 picometer or 10 to the negative 10th meter. And also the size of the nucleus is 0.001 picometer. So what does that tell you? It tells us if the size of the atom is 100 picometer, the size of the nucleus is extremely small at the center. Okay, one is 100, another one is 1,000. So the difference is what? The difference is almost 10,000 difference in size. So different size. So this picture tells us, compared to the size of the atom, which is small, of course, but the size of the nucleus is extremely small. So almost all atom is filled with what? Filled with electrons, because the size of the nucleus is small. Even though it is small, again, we know it carries all the mass because proton and neutrons carry the mass. So here is a comparison. Okay, I may not be extremely accurate, but here's a comparison to give you the idea of the size. If the size of the atom were the volume of a stadium, then the size of the nucleus will be a glass bead, okay, of the size of a glass bead, that's small, okay, compared to the size of the atom. So this again gives an idea, compared to the size of the atom, the size of the nucleus is extremely small. However, the nucleus itself, even though small, it carries almost all the mass of an atom because that's where protons and neutrons are located. Okay, so now after we know the anatomy of the atom, we know the particles, we know the charge and the mass, how do we represent an atom of an element? Okay, how do we put on paper, show, hey, this is an element and we want to demonstrate the numbers of these particles? We have a very special symbol notations used commonly in chemistry. Okay, this symbol is shown here. Okay, symbol is shown here. First, of course, you put the symbol of the element. Okay, the symbol of the element as the symbol. Okay, symbol of the element we learn in chapter 1, either be a capital letter or a capital letter followed by a lowercase letter. Now, on the left side of the symbol, you're putting two numbers as a superscript and a subscript on the left side. Okay, the subscript number is called a Z number. Okay, Z number, we call that number the atomic number. Okay, the atomic number basically tells people the number of protons. Okay, 10 number of protons. So the subscript on the left is called the proton number, or we call that atomic number. And later on, we're going to find out we can easily tell, or we can easily know the atomic number or proton number by looking at the periodic table, because elements in the periodic table is actually arranged in the order of increasing proton numbers or in the order of increasing atomic numbers. So we can find the proton number or atomic number directly from the periodic table. That's how elements are arranged. We're going to see that again in a short time. Okay, now after we know the atomic number as a subscript, let's take a look at the top number, the A number. Okay, the A number is a superscript. Okay, we call that number mass number. Okay, mass number. Now, if you remember, we talked about earlier, what is mass? Mass is the nucleus, right? The mass of an atom is concentrated at the nucleus. So the mass number basically means the mass of proton and neutrons, because that's the particles inside the nucleus. So the mass number basically equal to the sum of the number of protons and sum of the proton and neutrons. That's how we can know the mass number. Again, of course, we can easily tell the proton number. If we know the mass number, we can use this subtraction, subtract the proton number from the mass number. We can know the number of neutrons if needed, right? Because mass is proton plus, okay, mass number. Okay, mass number is proton, right? So if we subtract, okay, if we subtract proton number from the mass number, we can get the number of neutrons. Okay, this is some, how do we play with the mathematics of these numbers? But again, this is the common notation we use. Okay, common notation we use in our notation of these atoms, indicating the number of the symbol, the number of protons, and also the number of proton plus neutrons. We call that again the mass number. Okay, the mass number. Okay, a very quick check. Okay, the atomic number Z, okay, is what? The atomic number Z is basically the number of the sum number of protons in the nucleus of an atom. So answer is 8. We know that. Okay. Oops. Okay, sorry. Okay, the answer is 8, because we know the atomic number is the sum number of protons in the nucleus. The atomic number is the number of protons. Okay, next. Now, after we know what atoms is about. Okay, the atoms is about proton, neutron, and electrons. Now we have a new definition of atoms, of elements. Remember, in the first chapter we studied pure substance can be classified into elements and compounds. So now we have a new definition of elements. What are elements? We know elements are pure substances in which all atoms are the same, or of the atoms are the same type. So what does it mean, the same type of atoms? If atoms are the same type, means those atoms must have the same number of proton. Okay, because proton number is called atomic number. Means what? The number of proton specify what type of atom it is. Okay, again, element are pure substances with the same number of atoms. Means those pure substances, the atoms must be the same type. What does it mean, the same type? Same type means those atoms must have the same proton number. Okay, because proton number is called the atomic number. Atomic number specify the number of proton, the type of atoms. So elements are the pure substance in which all the atoms have the same proton number, or of course, the atomic number. Okay, atomic number. That is why we said in our periodic table, the elements are arranged in the order of increasing proton numbers. Each element has a specific proton number, or we call it atomic number. Okay, so here is more about an atom. Okay, or an atom. Now we know atoms. Okay, atoms of the same type have the same number of protons because they are the same type, they are the same element. So the number of protons must be the same. However, we did not say the number of neutrons must be the same. Okay, must be. In fact, atoms of the same type may not have the same number of neutrons. And those atoms with the same number of protons but different number of neutrons, we call those atoms isotopes. Okay, isotopes. Isotopes are the same element because the number of protons will be the same, but the number of protons, neutrons will be different. Now, if you know that the number of proton, okay, number of proton plus number of neutron is the mass number. So if the number of protons is the same, the number of the neutrons are different. This means what? These isotopes, their mass numbers will be different. Okay, for example, in the following picture, I have 3 isotopes of carbon. Carbon-12, carbon-13, and carbon-14. Okay, carbon-12 means the mass number is 12. Okay, mass number is 12. If mass number is 12, we know carbon is number 6 element. If you look at the periodic table now, you can pause, look at the periodic table, you will see that carbon is number 6. Number 6 means what? The atomic number is 6. Atomic number 6 means the proton number is 6. So 6 proton, if the mass number is 12, means what? The neutron is also 6. So this carbon-12 has 6 protons and 6 neutrons. The second one, carbon isotope, is called carbon-13. Okay, carbon-13. Same, it is carbon. So the number of proton is also 6. However, because the mass number is 13, we know the number of neutron is 7. And of course, the last one, carbon-14, still 6 protons, but 8 neutrons. You can see that these 3 carbon isotopes of the same carbon element, but different number of protons resulting in different number of masses. Okay, masses. And these isotopes, generally, they have very or identical chemical properties. Okay, the only difference between these two are these two have different masses. Okay, different masses. And also the isotopes, okay, the isotopes in nature of the same element come in different percentages. We'll talk about that in a very short time. And that percentage is called natural abundance. Okay, they don't exist in the same percentage. For example, the carbon isotopes. The most abundant carbon isotope is carbon-12, which is around 99%. Carbon-13 around 1%. Carbon-14, which is radioactive, is actually less than 1%. Okay, less than 1%. So that is isotopes of the same element, same proton number. Okay, here is more practice showing you the isotopes of silicon. You can see that silicon, this is the notation we just talked about. Okay, the symbol, the subscript, and the superscript. We know the symbol is silicon. The subscript is the number of protons. So both silicon isotope have the same number of protons, 14, right? Because silicon is number 14 element if you look at the periodic table now. Okay, but these two silicons will be different. Okay, one silicon is 28, another silicon is silicon 29. So that means these two silicon have different number of neutrons. The first silicon have 14 neutrons, the second silicon atom has 15 neutrons. That is why the number of mass will be different. It will be different. And by the way, okay, we haven't mentioned that, we haven't practiced that, but you know that both the silicons, because the proton number is different, proton number is the same, 14, so their electron number also must be the same, right? Number of proton equal to number of electrons. Don't forget that. Okay, electrons equal to the proton number. If the proton number are the same, 14, so each silicon atom has 14 electrons as well. Okay, electron as well. Okay. Here is a quick practice. Okay, practice asking you the 3 isotopes of something. Okay, something. This is the composition of a gas. Okay, and these 3 isotopes will be used in different applications. Okay, they all have the same atomic number, but the number of neutrons will be 0, 1, and 2. Okay, when you read here, the number of neutrons is 0, 1, and 2. You will know that the isotope will be hydrogen isotope, because hydrogen 1, okay, hydrogen 1 will be the one without any neutrons, okay, without neutrons, hydrogen 1, or you can put this notation 1 and 1. Okay, this is the notation of hydrogen 1. That means this hydrogen has 1 proton, and the mass number is also 1. That means the mass comes from that proton, and there's no neutrons. Okay, if you read that, you know the isotopes will be hydrogen. Okay, because hydrogen are the one, I think the only one without neutrons. Okay, so the number of neutrons 0, 1, and 2 are hydrogen isotopes. That means the other 2 isotopes will be hydrogen 2 and hydrogen 3. So these 3 are the hydrogens. Again, you can see they're all hydrogen. The proton number is always 1 because hydrogen is the first element, but the number of neutrons is 0, 1, and 2. So the mass number will be 1 and 2 and 3. Okay, those are the 3 hydrogen isotopes. And we have a name for those 3 hydrogen isotopes. We call those protium, deuterium, and tritium. Okay, so answer is B. Okay, answer B. And those 3 isotopes are actually very commonly used in all kinds of applications besides the hydrogen gas, but deuterium or heavy hydrogen or tritium, hydrogen 3, which is radioactive, are all in all kinds of applications. Okay, this is a tritium tube. Okay, tube contains tritium gas, which is radioactive, will hit the fluorescence materials, so you can get it. The tube gets lighted up. Called a tritium radioluminescence. Okay, that's one of the applications for tritium, because utilizing the radioactivity, and you can read more about the radioactivity of or more applications of these 3 hydrogen isotopes. Okay, isotopes. And here's another practice. I wanted you to use it as a practice, understanding okay, the numbers, proton number, neutron number, the mass number, and also use which number to identify the element. Okay, so use this as a practice yourself after the lecture. Okay, after the lecture. Okay, let's keep moving. Excuse me. We know atoms of the same element come in different isotopes. Okay, isotopes. And isotopes are the one with different mass numbers. And we also know, okay, different isotopes come in different percentages. Okay, some isotopes are more abundant, some isotopes are not that much abundant. So that means each element, when they're present in nature, they are existing as a mixture of all kinds of isotopes. And the isotope will come in different percentages, of course, different masses. Isotopes do have different masses. So like you see in this chart, this is from 1 to 12 elements, from hydrogen to magnesium. These first 12 elements, most of them come in different isotopes except beryllium and fluorine. So you can see that hydrogen or lithium or nitrogen, when they exist as a mixture of these isotopes. Okay, lithium, 2 isotopes. One is lithium 6, another one is lithium 7. Okay, lithium-6, the mass number is 6, lithium-7, the mass number is 7. But when you have a mixture of it, okay, mixture of it, how do we know the mass of that element? Because it exists as a mixture, right? One is 6, one is 7. And they also come in different percentages. The mass number with 7 has a greater percentage. The mass number of 6 has a smaller percentage. So how do we know the mass of the element? Or in another way, how the mass number in the periodic table is calculated? Remember, in our periodic table, we have two numbers, more important numbers. One is, again, the proton number. You can see that the top number in this periodic table is called the proton number. Proton number means what? The atomic number. But the number at the bottom of the element, for each element, is called what? It's called the atomic mass. What is atomic mass? The atomic mass is the mass of that element. Is the mass of the element called atomic mass. So how the mass of each element is calculated? Remember, element exists as what? As a mixture, okay, of different masses. Okay, carbon has 3 masses, lithium has 2 masses, and each mass having different percentages. So know the mass of that particular element. How do we average it? This is what our topic. But again, 2 mass definitions. One is called the mass number of each atom. Lithium-6, mass number is 6. Lithium-7, mass number is 7. But when it comes to periodic table, you can see there's a mass under lithium, 6.939. That mass is no longer called mass number. It's called the atomic mass. Okay, this is the mass of lithium. Okay, lithium. Like we said, lithium exists as a mixture, so we have to do some kind of average calculation to calculate the average mass of these 2 isotopes of lithium. So what is atomic mass? Atomic mass in the periodic table, shown in the periodic table, is actually the calculated average mass for all the isotopes of the element. Okay, if you have 2 isotopes, 3 isotopes, you're going to calculate the average. But keep in mind, these isotopes do not exist in equal amount. Some has more, some has less. So you can not simply add them together, divide by 2 or divide by 3. That's not average because they don't come in the same percentage. Some are more abundant, some are less abundant. Okay, but here, first, know these 2 terms. The mass number, which is the superscript, is the mass of that single atom. The atomic mass in your periodic table is the calculated average mass for the isotopes of an element. Okay, don't confuse these 2 mass. Okay, 2 mass. And here we're going to talk about how do we calculate the mass of that element? How are these numbers calculated? Okay, here is the practice. Okay, there are 2 solutions. Okay, 2 solutions. One solution is shown here. Okay, I'm going to show you the second one. Okay, you can use either one, whichever you feel is more understanding. Okay, the question here is chlorine consists of 2 isotopes. One isotope has a mass around 35. Okay, the percentage of that is 75.77. Another chlorine has a mass number of 37, around 37, and the percentage of it is 24.223. So you can total is 100%. So you have 2 isotopes. One is around mass of 37, another one is 35. Each one has a different percentage. So you want to calculate the average atomic mass of chlorine. So how do we calculate it? This is the first solution shown here. You use the mass, multiply the percentage to get the mass contribution of that isotope. Okay, one has a mass of 35 here, around 35. You have to carry the whole number, 34.96885. Then you multiply the percentage of it and get a number. And that number is what? Is how much mass is contributed from that particular isotope with 75.77%. And you do that again, use the another mass multiplied by the percentage, you get what? You get another contribution of the second isotope. And then you add these 2 contributions together, you get the average mass, 35.45. You can see that that's the average mass of chlorine, 35.45. And you can see this calculation consider both factors. One factor is, of course, the mass of each isotope. Another factor is what? Is their percentage. Remember, they don't exist in the equal amount. So you have to ask, what is the contribution of each? Okay, this is solution one. I think this is an easier solution. Okay, easier solution, very straightforward. Use the mass multiplied by percentage and add them together. Okay, another solution, which I think you can understand a little more. Okay, because it's an average. So let's say we assume we have 100 atoms. If we have 100 atoms, then I use the total number of atoms multiplied by the percentage. I can get the actual number of the atoms. Okay, sorry, let's come back. Okay, the second one is we assume we have 100 atoms. Then I use the total number of atoms multiplied by the percentage. I get the actual number of atoms. So the one with 35 mass, around 35 mass, the actual number is 75. Okay, 75. The other one, the actual number is 24 because you use total 100 multiply the percentage. Then we do the average. We use mass of each multiplied by the number, and we use a mass of each multiplied by the number, we get the total mass, right? The mass of 34.9 something multiply the number, so we get the total mass of that guy. And then we use 36 point something times the number, we get the total mass of that guy. So add them together, I get the total mass, then divide by the total number. Remember, we call it average, right? Total mass divided by total number. Total number is 100. We assume we have 100 atoms, and then we get the same. Okay, we get the same average mass, atomic mass. Okay, so again, these two are different solutions. Okay, I like the first solution, but you can use second solution either way. Okay, here is a practice for you. Okay, the second solution is shown here, but the first solution I want you to work on your own and see if you can understand the calculation. If you have any questions, you can always feel free to ask or a solution. Okay, for a solution. But again, two solutions, both consider two factors, the mass number of each isotope and also the percentage of each isotope. And you remember, after you calculate that, what you have in the periodic table will be called the atomic mass of that element. Okay, that is not a mass of each single element. Each single atom, that is the mass of called an average. Okay, an average mass. Okay, so that's numbers. Okay, after that, let's take a look at our periodic table. Okay, like I said, we're going to introduce our periodic table briefly in this chapter, giving an overview of this table. Okay, we have seen a few times, or you have a periodic table in front of you. We know that periodic table already. The elements in the table are arranged in the order of increasing atomic number. Okay, increasing atomic number or number of protons. And after you do that, you find out elements with similar properties will be positioned columns. Okay, or position, or you can see that it will be like in a cycle. Okay, elements of similar properties are always falling in the same column. So we're going to see some examples, and also we're going to give the terms of the table. The row of the element, okay, when you move from left to right, are called the periods. Okay, the horizontal rows are called periods. In our modern periodic table, we have 7 periods, period 1 through 7. The vertical columns in which elements with similar properties are arranged are called groups. In our modern periodic table, we have 18 groups, okay, 1 through 18. So here is the periodic table. You can see we have 7 periods and we have 18 groups. Okay, 18 groups. Of course, if you notice that the periodic table shown here, the group number, not only numbered from 1 all the way through 18, there's another group number below it. The group 1, 2, and 13 through 18. Okay, group 1 and 2, 13 through 18. These groups, these 8 groups, are actually called A groups. Okay, A groups. So we actually number these 8 groups from 1A to 8A. Again, these groups are called A groups. And the other groups are called B groups. Okay, so there are 2 numbering systems for the groups of the periodic table, 1 through 18, or groups 1, 2, and then from 13 all the way to 18, these 8 groups are called A groups. Okay, A groups. Keep that in mind. We're going to use that later, that numbering system, especially the A group numbering system later. And like we said, elements with similar chemical properties are falling in under the same column, in the same column. So here I want to show you the 4 most typical groups. Okay, typical means those elements are so similar in chemical properties wise. Okay, very typical. Those 4 groups are so typical that we even give these groups a name, the group name for the element in these groups. And those 4 groups are, you can see that shown in this small periodic table, 1A, 2A, right? Number 1 and number 2 group. And then 7A and 8A, which is number 17 group and 18 group. So make sure, again, you can double check the periodic table. 1A, 2A is 1 and 2. 7A, 8A is 17 and 18 group. Okay, these 4 groups are so special, we even give them names of the group. And then we're going to briefly take a look at the elements in these groups. Okay, these 4 groups, the names are alkali metal for group 1, alkaline earth metal for group 2, halogens for group 7, 7A, and noble gases for group 8, 8A. Okay, first, this is a picture showing you the 3 of the alkali metals, group 1 and metals, lithium, sodium, and potassium. And you notice that these metals are stored in a liquid, and that liquid is actually mineral oil. Okay, mineral oil. The reason they have to be stored in oil, because these metals are super reactive. They will easily react with air, moisture in the air, and oxygen in the air to react. So in order to avoid contact of the air, we have to store them in mineral oil. And of course, you can see lithium even floats in mineral oil because lithium is very lightweight. The density of lithium is very small. Remember we learned in chapter 2? And because of that property, lithium is very commonly used in batteries. Okay, you guys use cell phone and battery or laptop batteries, or even EV cars battery. They're lithium ion or lithium polymer batteries. Okay, the second group, 2A, are called alkaline earth metals, including beryllium, magnesium, calcium, strontium, and barium. These metals are also reactive, but not as reactive as group 1A. Among these, strontium and barium are so reactive, they also need to be stored in oil or avoid contacting with air. Group 7A are called halogens. This is the group of diatomic molecules. Okay, element in these groups, in this group halogen, exist as diatomic, mean X2. Fluorine is F2, chlorine is CO2, Br is Br2, iodine is I2. They all exist as diatomic molecules. And these elements come in different physical state. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Okay, very interesting. And these gases, or solid and liquid, they are all highly reactive. And the last group, noble gases. helium, argon, krypton, xenon, neon. These gases are called noble gases. The reason they're called noble gases because these gases, all of them, are very unreactive, inert. Okay, inert. And that is the property of 8A elements. Okay, again, this is a very brief view. We're going to study them and see the reaction of them throughout this course. Okay, a very quick check. Elements are arranged in the periodic table according to what? The increasing number of protons, and we call that atomic number. So our answer is C, right? So next, the elements, 118 elements in our periodic table can be classified in different ways. The first classification is based on some selected physical properties. Okay, if you guys remember, when we talk about the term physical property means what? The property that are not involved or not observed in chemical reaction. That means these properties don't change the identity. Okay, physical properties. Based on the physical properties of the elements, we can classify the element into two big categories or three big categories. Okay, metals and non-metals. And there's a line joining here in our periodic table. Okay, on the right side of the periodic table, there's a line. You can see the zigzag line, and that line separates metals and non-metals. Non-metals are the blue ones on the top right corner. Metals are the gray ones at the bottom left corner. Of course, we have more metals than non-metals. Okay, if you look at the periodic table, if you draw a line there, okay, here is the line. You see the line here, zigzag line, and you can see that on the bottom left corners are metals, and the top right corners are non-metals. Okay, the reason here we have two or three big categories because the elements on the line, like silicon, Ge, arsenic, and these elements, sometimes they bear the property of both metals and non-metals. So we call some of these elements metalloids. Okay, there's something between. That's why we call them like the two or three big categories. Normally, two big categories, metal, non-metal, but elements on the line, along the lines, sometimes they bear the property of both groups, and we call those metalloids. Okay, we don't talk too much about metalloids in this class, but you know the classifications. Okay, but now, what are these physical properties assigned to metals versus non-metals? Are shown here. Metals, usually, okay, just like your regular normal understanding about metals, usually what? A luster. They conduct heat and electricity very well, and they have great malleability, means you can make them different shapes, like beads, fillings, a film, or strips. You can change different shapes, and all metals are solid except mercury. Okay, these are some typical physical property of metals. On the other hand, non-metals means what? They don't have these elements called non-metals, don't have these properties. Okay, they're absent of the metal properties. So it means they can be liquid, they can be solid, they can be gas. They don't take in a certain shape. Okay, they don't conduct electricity or heat well. They're mostly brittle. Okay, they're not malleable, etc. So these are called non-metals, means they're not metals. So based on the physical property of the elements, we classify our elements into two types. Again, there may be a third type along the lines, the elements along the lines. Another classification is based on electron configuration. Okay, you might wonder, what is electron configuration? Don't worry, that's our topic in the second half of this chapter. Okay, electron configuration. Based on that, we classify the elements into 4 groups. Okay, 4, you can see we separate the periodic table into 4 blocks, 4 groups. Group 1, 2, 13 through 17, or 1A through 7A. These groups are called representative elements or main group elements. Group 18 or 8A are called noble gases. We know they're called noble gases already. Elements here, B groups, including transition element and inner transition element. Okay, transition, you know, is kind of like a transit between metal and metal, kind of like a transition element. But what is inner transition? If you notice that for period 6 and 7, between these 2 elements and between these 2 elements, you can see that the atomic number is jumped from 57 to 72, or jumped from 89 to 104, right? There's a big jump. That means some elements is missing here. That's how these 2 are inserted into these P2 periods. And that's why we call these elements inner transition elements. Most of them are radioactive elements, are synthesized. Okay, most of them are synthesized radioactive elements. Okay, some are naturally existing, but most of them are radioactive elements. So this is how we classify the periodic elements based on electron configuration. Again, of course, we're going to answer that. What is electron configuration? But here you should know what these groups are called. Group 1 through 7, or 1, 2, 13, 14, 15, 16, 17. These groups are called representative groups element. Noble gas, transition elements, and inner transition elements, which is inserted in period 6 and 7 for inner transition. Okay, in this class, we study mostly representative elements and noble gases. Okay, that's our focus for this class. But we do come across some transition metals. Okay, we do see some transition metals or compounds containing these transition metals. Okay, normally we don't talk about inner transition metals. And besides that, okay, even though it is not our focus of this class, transition metals play a key role in our biological systems. A lot of transition metals are key components of our enzymes, serving as cofactors of our enzymes. Okay, if you study biochemistry, you will know that you will see a lot of these transition metals like manganese, iron, cobalt, zinc, etc. Okay, they are present in our human body as trace minerals. Okay, trace minerals. So that is the first part of this chapter. Okay, if you want to take a break, you can pause the video and study some and take a break. And after that, we're going to take a look at the second part of this chapter, how electrons are arranged within an atom. We know electrons are filled in the empty space of an atom, but that filling is very abstract. How do they fill in? Okay, how the electrons are placed in the empty space, within the empty space, and what is called electron configuration. Remember, we talked about that in the first part. And here is our topic. Okay, please follow with me, because follow me the flow, because this part is very abstract, because we cannot see the atom. Okay, we have to use our a logic to see, oh, how do we place electrons, fill electrons in the empty space? But let's take a look. What is the empty space? How the empty space outside the nucleus are divided. Okay, the empty space outside the nucleus is divided by different levels, okay, different energy levels. And that different energy level is called the shell, okay, or shells. Shells is a region around the nucleus that contains electrons with approximately same energy, means energy in the shell will have similar energy. That's called energy level. Okay, energy level. You can see this is a picture showing you what the shell approximately look like. It's not an accurate term, okay, but kind of like show you what shells are different energy levels outside the nucleus. Of course, electrons that are in the first energy level, means close to the nucleus, will have lower energy. Electrons moving away from the nucleus will have higher energy. Why? Because if you want to pull energy away from the nucleus, pull some negative away from the positive, you need energy to do that. So lower shell, okay, lower shell has lower energy. Away from the nucleus, energy higher. Okay, but shell is called energy level. That's how the empty space are divided. First level is shell. Electrons within the same shell have approximately the same energy. Approximately. Later on, we're going to see that. Now, each shell, okay, each shell, the region within each shell can be further divided into subshells. Subshell are regions within a shell that electrons now contain the same energy. So shell is electron have approximately same energy, but each shell can be divided into subshells. And electrons in the subshells now have the same energy. Okay, same energy. And if you look at the picture shown here, the first shell, okay, the first shell have one subshell. We call the subshell S subshell. And because it belongs to the first shell, we call that subshell 1s. The second shell has two subshells. And those two subshells are called S and P. And because they both belong to second shell, we call that 2s and 2p. The third shell have three subshells, S, P, and D. And because they both belong to the third shell, we call those subshells 3s, 3p, and 3d. And the fourth shell contains four subshells. We call that S, P, D, and F. And because they all belong to the fourth shell, we call those subshells 4s, 4p, 4d, and 4f. So now you can see that we can actually tell the number of subshells in each shell because the number of the subshells equal to the shell number, right? Shell number 1 has one subshell. Shell number 2 has two subshells. Shell number 3 have what? 3 subshells. Shell number 4 have 4 subshells. And the subshells are named by letters, S, P, D, and F. Of course, in front of letter, we put the shell number. If the S belong to first shell, it's called 1s. If the S belong to shell 2, we call that 2s. If shell S belong to 3, we call it 3s. But the number of subshells is determined by the number of shell. The same as number of shell. Okay, keep in mind this picture, very important. What is shell energy level? Within each shell, there are subshells, and the number of subshells equal to the shell number. And how do we designate the subshells? 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, these are subshells. And move on. Okay, that's why please follow me. This is very some abstract information. Within each subshells, okay, within each subshells, there are further divisions called orbitals. Okay, orbitals. What is orbital? What does this word mean? We know satellites, they move around, for example, our planet Earth in a very designated orbit, right? Like oval orbit. We know the path. We can calculate the path. But electrons, okay, electrons, the path of the electrons are way more complicated. They don't move in a predicted path, orbit. They're actually probabilities moving in the empty space of the nucleus. So we give a new term. Instead of orbit, we can predict. We call them orbitals. That's how electrons are moved or located, called orbitals. The region within a subshell where electrons can be found. Again, electrons are not predictable, so we cannot know the exact paths. So orbitals are basically regions within a subshell. Okay, shell, subshell, and orbital. Okay, orbitals. Orbitals are something within the subshell where electrons can be found. Okay, can be found. Now, here this table shows you the number of orbitals. For S subshell, no matter 1s or 2s or 3s, okay, as long as it's S, remember subshells are designated by letters. Okay, subshells are designated by letters. Of course, in front of letter, there's a shell number, but subshells are by letters, S, P, D, and F. For S subshell, 1s, 2s, 3s, 4s, doesn't matter. There's only one orbital. And each orbital can accommodate 2 electrons. So subshell total can only accommodate 2 electrons for S subshells. Okay, because no matter what, S subshell only is one orbital accommodate 2 electrons. Next, P subshells. No matter 2p, 3p, 4p, there's no 1p. Okay, first shell doesn't have p. P subshells have 3 orbitals. Each orbital will accommodate 2 electrons, so 3 orbitals will accommodate what? 6 electrons. So P subshells can maximally accommodate electrons. D subshells, 3D and 4D. Okay, 3D and 4D. There's no 2D. Okay, second shell doesn't have D subshell. Okay, D subshells have 5 orbitals. Each orbital has 2 electrons, so 5 orbital D subshell can hold what? 10 electrons. And finally, F subshell for F has 7 orbitals. And each orbital has 2 electrons, so 7 is 14 electrons. So this picture shows you the number of electrons can be held in each subshell because the presence of what? Different number of orbitals. S subshell, 1 orbital. P subshell, 3 orbitals. D subshell, 5 orbitals. F subshell, 7 orbitals. Each orbital has 2 electrons. No matter which orbital has 2 electrons. So with that, this is what we have learned so far about the dividing the empty space outside the nucleus. And this will be how the electrons will be filled. The space where electron will be filled. Okay, let's review one more time. I want you to be very crystal clear about this picture. The empty space is divided by shell, okay, energy level. Electrons in these shells have approximately the same energy. Okay, lower shell, lower energy. Shell 1, 2, 3, 4. Okay, there are higher shells, but we normally don't use them to fill electrons. Electrons are mostly filled in these 4 shells. And then each shell has subshells. The number of subshells determined by the shell number. First shell, 1 subshell, we call it 1s. Second shell, 2s, 2p. Third shell, 3s, 3p, 3d. Fourth shell, 4s, 4p, 4d, 4f. Okay, these are the subshells. And subshells contains what? Orbitals. Okay, orbitals. S subshell, 1 orbital. So you can see that S subshell can hold what? 2 electrons, no matter 1s, 2s, 3s, 4s. P subshell, 3 orbitals. So P subshell can hold what? 6 electrons. D subshell, 5 orbitals. So D subshell can hold 10 electrons, no better than 3d or 4d. And finally, F subshell, 7 orbitals, 14 electrons. Okay, 14 electrons. And this is how these are divided. Okay, divided. And like we said, orbitals are actually where electrons can be found. So I want to show you a picture of a few orbitals. You get an idea why S subshell only has 1 orbital. P subshell have 3 orbitals. Okay, I want to give you a picture of the orbitals. Orbitals, again, are where electrons can be found. Okay, they're not in the path. They're actually probabilities where they can be found. So this is the picture of the orbitals. S orbital is a sphere, like a ball. P orbital, like 2 balloons tied together. D orbital is like 4 balloons tied together. F orbital is like 8 balloons tied together at the center. Okay, these are what electron orbitals are looking like. Okay, this is the picture of the 3 p orbitals. 3 of the p, or remember, p subshell has 3 orbitals. Okay, this is 3 of them. You can see they all look the same. 2 balloons. P subshells are like 2 balloons, but they are pointing different directions. One is along the x-axis, another one is along the y-axis, another one is along the z-axis. So basically, 3 of those p are like this. They're perpendicular to each other, if you guys notice. Okay, they're perpendicular to each other. Okay, one is x, another one is y, another one is z. So that's how p orbital has, p subshells have 3 orbitals. They're py, px, pz. Okay, of course, shell, subshell, they contain orbitals. They are arranged in the order of increasing energies, so electrons can be filled in. So something like that is called the orbital diagram. Okay, orbital diagram. This is just a small part of it, but you can see, get an idea. The first energy level has 1 subshell with 1 orbital. That's why we use a tiny square to indicate that orbital, 1s. The second subshell, the second main shell, second level, has 2 subshells, 2s and 2p. 2s, 1 orbital, 1 square. 2p, we know p has 3 orbitals, so we put 3 squares. See that? The third shell, okay, third shell, we have 3 subshells, 3s, 3p, and also 3d. Someone, why, where's the 3d? Why don't you show 3d? 3d is in fact in higher energy above 4s. That's why 3d is over here. That's why we didn't show, we only showed part of it, but we will show that later. But this is how the orbitals are arranged in the order of increasing energy. Later on, we're going to study, we're going to put electrons in these orbitals. Okay, in lectures, but I want to give you an idea of what these shell or ball shell are useful. They're used to fill in electrons. Okay, we'll do that, okay, in a few minutes. And next, I want to also briefly talk about a concept we talked about earlier, is 1 orbital only can accommodate what? 2 electrons, right? Each orbital contains, no matter what orbital, 1s, 2p, 3d, each one orbital can only accommodate 2 electrons. Why is that? The reason is electrons are spinning. Okay, electrons are spinning. Electrons are moved in the empty space of outside nucleus, but also themselves are spinning, either clockwise or counterclockwise. They're like magnetic balls, like our Earth. But they can spin in 2 directions, clockwise or counterclockwise. Okay, counterclockwise. When electrons are present in the same orbital, their spinning must be opposite. So 2 electrons fill in the same orbital, they must have opposite spin. There's no third way, because they must be different. Okay, one of the term of them must be different. If everything is the same, energy is the same of the electron, they have the same shell, same subshell, same orbital, everything is the same, then they must be something different. their spin must be different. You cannot have a third electron. A third electron will either have a same spin as either one of those. So that is why orbital can only accommodate 2 electrons, because one term of those 2 electrons must be different spinning. If electrons are in the same orbital, everything is the same except the spinning will be different. And that's called Pauli's exclusion principle. You can read more. I have a note providing it. Okay, but again, the concept is each orbital, no matter what orbital, no matter it belongs to which subshell, can only accommodate maximally 2 electrons. Okay, 2 electrons. Okay, this is a quick concept check. You can quickly answer the question yourself, I think. And here is another picture showing you what we have talked about, the overview. Like I said, very important. Okay, you know these terms. Shell, energy level, 1, 2, 3, 4. Each shell have subshells. Okay, the number of subshells is the same of the shell number. Okay, first subshell, second subshell, third subshell, and fourth subshell. Okay, subshells are designated by numbers S, P, D, and F. Of course, we put letters S, P, D, and F. And of course, we put a number in front of the letter to indicate which shell does it belong to. And then each subshell has different number of orbitals. S subshell, 1 orbital. P subshell, 3 orbitals. F subshell, 5 orbitals. And D subshell, 5 orbitals. F subshell, 7 orbitals. And each orbital will accommodate 2 electrons. So S subshell, 2 electrons. P subshell, 6 electrons. D subshell, 10 electrons. F subshell, 17 electrons. Okay, 17 electrons. So again, no matter which picture you prefer, make sure you understand shell, subshell, orbitals. Because we're going to fill in electrons in these orbitals now. And that filling process is called electron configuration. Once we know how electrons are filled in, we call that the configuration of the electrons in an atom. Now, there's 2 general rules we have first to show you, and there are a couple of more rules. But here, first, the general rules, when you fill in electrons in these orbitals, remember, orbitals are where electrons are filled. When you fill in the electrons in the orbitals, you fill the electrons from the lower energy orbital, then move up to the higher ones. You have to fill in the lower ones and then move up to higher ones. Remember, each orbital can only accommodate 2. So you keep filling until it is full, and then move up to the higher energy. From lower energy to higher are filled in the increasing energy order. That's the first rule. The second rule is something we already mentioned. Each orbital, remember, you can only fill 2 electrons, and those 2 electrons must have opposite spins. Okay, I will show you a way. How do we show the opposite spin? Very simple, okay, in a couple of minutes. So keep in mind these 2 rules, and then take a look at the picture. This picture shows you the order of energy of the subshells. Okay, order of the energy of subshells. Order of energy means what? You have to fill in these subshells in this order. Remember, you filled in the increasing order. This is the energy of increasing order of the subshells. 1s, 2s, 2p, 3s, 3p. It normally is in the order of increasing shell, but you will see that there's some overlap between 3d and 4s. Okay, regarding these 2 subshells, 4s has lower energy than 3d. So you fill in 4s first, then 3d. Then after 3d, 4p again, there is some overlap between 4d and 5s. 5s is lower than 4d, so you fill in 5s first, then followed by 4d, then 5p. Okay, so this is the order of subshells. Okay, the most common mistake will be here. 4s has lower energy than 3d. After 3p is not 3d, it's 4s, energy-wise. Right? So let's take a look. How do we feel electrons in the orbitals? Okay, the first example is our first element. Is that we're feeling electrons for the atoms. And the first element we choose was the first element in our periodic table, hydrogen. Hydrogen is the first element, means one proton, one electron. The first electron has to go to the lowest energy one, right? 1s. So in that case, we put one electron in the 1s orbital. We use that as a superscript. See that? 1s1. And that one means electron. Okay, the superscript electron. That's called the electron configuration of hydrogen. Easy, right? 1s orbital has one electron. Or 1s subshell has one electron in 1s orbital. And of course, we know we use a square to demonstrate that orbital. And you put an electron as an arrow inside the orbital. And we call this orbital diagram. The orbital diagram. Okay, you have to know both. Depends on what the questions are asking you to do. Okay, the left one is called electron configuration, showing one electron in the 1s subshell, 1s orbital. The right one, you use a square to represent the orbital, 1s, and then put an arrow to represent the electron. One electron, just one. Move up. Helium, the second element, now have two electrons. We know each orbital can accommodate two electrons, so we can put both electrons of helium in the same orbital, 1s. So now 1s becomes 1s2. Okay, 1s become 1s2. Right, superscript 2 again represent electrons. And the orbital diagram will be two electrons in the square, but now you see that these two electrons are opposite. Okay, opposite. Usually, arrows wise, we use single head arrow. Okay, single head arrow, but double header arrow is okay. There's no right one. I've seen both, but usually, okay, I prefer single head arrow showing one electron. So you can see that these two arrows are opposite, showing what? Opposite spin in the same orbital. 1s orbital again can accommodate two electrons, so you can put both electrons in the same orbital. That's our helium. Move up. Lithium has 3 electrons, so you put 2 in 1s. The third one cannot go to 1s because 1s is full. Only 1s can only have 2 electrons. So the third one goes to 2s. Remember the order? 1s, 2s, 2p, 3s, 3p. So after 1s, the third one goes to 2s. So 1s2 and 2s1, 3 electrons. And the left is the orbital diagram. 2 electrons in 1s opposite, and the third electron in 2s. The fourth one, beryllium, 4 electrons, 2 in 1s, 2 in 2s. So 1s2, 2s2. And you can see that 2 electrons in the 1s, 2 electrons in the 2s are both opposite spin. Number 5, boron, 5 electrons, 1s2, 2s2, and then the 5th electron goes to 2p now, right? Remember, p has 3 orbitals, so you have to put 3 squares for p. Okay, p subshell has 3 orbitals, so you have to put 3 squares for p. Of course, for boron, the 5th electron goes to one of the p orbitals. Okay, one of the 2p orbitals. Now, if we think about it, after boron will be what? Will be carbon, right? Carbon has 6 electrons because carbon is number 6. So that means you need to add 1 more electron to the 2p. The first 2 will be the same for carbon. So the question comes, do you add electron to the 2p that is already half occupied, or you add the electron, the 1 extra electron of carbon to a new 2p? Remember, you have empty rooms, right? There are 2 ways of adding that number 6 electron. The first 5 are the same as boron. for carbon. The first 5 is the same as boron. The 6th electron can either go to the one with electrons inside, because each orbit can hold 2, or go to a separate room, like 2 people share the same room, or they go to 2 separate rooms. Okay, which way is that? We in fact have a rule, okay, the third rule. Electrons will occupy orbitals singly first to the maximum extent possible before they pair. So that means for carbon, you can see that these 2 electrons will occupy orbitals singly. They're not sharing yet the same orbital. Okay. And if they occupy the orbital singly, the spin must be the same. They must adopt the same spin. Okay, because both arrows in these 2 p's are pointing the same direction. Okay, this is very important 2 rules. First, if you have available subshell of the same energy, the electrons will occupy the orbitals singly to the maximum extent until you don't have available. And then when the electrons occupy the orbital singly, they have to occupy the orbitals in the same spin. Okay, that's for carbon. So 1s2, 2s2, 2p2. But remember, in this 2p2, those 2 electrons are like this. Singly, unpaired. Okay, singly unpaired. Followed by nitrogen, followed by carbon is nitrogen, 7 electrons. You can see that. 1s2, 2s2, and then 2p3. Okay, 2p3, those 3 electrons are all occupying the orbitals singly. Okay, occupy singly. Okay, in the same spin. Now, after nitrogen will be oxygen. You guys think about the 8th electron goes where? The 8th electron doesn't have any empty room, but 2p is still available. 2p can hold 6 electrons, remember. So for nitrogen, the electron has to go what? For oxygen, the 8th electron has to go into pair. Okay, so let me show you in the empty space oxygen. I forgot they don't even include here. So let's do oxygen here. Okay, let me do oxygen here. Oxygen, 8 electrons. Okay, 8 electrons, 1s, 2s, 2p, 3s. Okay, so that's oxygen. We know 8 electrons. First one, second one, third one, fourth one, fifth one, sixth one, seventh one. Okay, there's the 7th one. The 8th one, again, there's no empty ones. You cannot go to 3s yet because 2p is still available. 2p can hold what? 6 electrons. So now the 8th one, let me change the color. Okay, the 8th one has to pair with one of them. Opposite spin. In the same orbital must be opposite spin, remember. Okay, opposite spin. So this is what oxygen looks like. And of course, the electron configuration will be 1s2, 2s2, 2p4. Okay, 2p4. Okay, I didn't realize they depend on oxygen and fluorine, and you can do fluorine. And after that, they have neon and sodium. Okay, these are some examples. Again, fill in the order of the subshells. Okay, with that logic, I hope you can use this chart to practice to fill in the electron configuration and orbital diagrams from magnesium to calcium. Okay, from 12th element for number 12 element to all the way to 20. Calcium is number 20 element. Okay, make sure you fill in this table. Okay, draw practice so you can get better. Okay, if you have any questions, we can practice, okay, in our recitation sections. Okay. Quick concept check. The electron configuration for sodium is 11th element, number 11, so 11 electrons. So we have 1s2, 2p2, 2p6. Okay, that's 10 already. Then after 2p6 is 3s1. Okay, 3s1. So answer is B. Okay, 11 electrons. After 2p6 is 3s. So 1s2, 2s2, 2p6, after that is 10. Then 1 extra goes to 3s. So 3s1. So answer is B. Answer is B. And here is the practice asking you to draw the electron configuration for each of the following. The first one is sulfur. The second one is barium. Okay, the second one is barium. So the first thing to do, of course, you need to know the number of protons. So you know the number of electrons. Okay, the first one, sulfur, the number of proton and electrons is 16. So if we know the number of 16, we can fill the electrons in these orbitals. Okay, you can follow me. 1s2, 2s2, 2p6. Okay, that's 10 now. Okay, after that, 2p6 is 3s2. That's 12 now. And then what? 3p4. Okay, 3p4. Okay, that is the number of electrons, 16. Okay, and the second element, beryllium. Okay, let's take a look. This is a periodic table very quick. Beryllium is 56 element. So beryllium has 56 electrons. So we're going to fill all these electrons in the order of subshells. Okay, please follow me. 1s2, 2s2, 2p6. That's 10 now. Okay, we have a long way to go. After 2p6 is 3s2, 3p6. Okay, after 3p6 is 4s. So 4s2. After 4s2 is 3d. Okay, 3d. We know d subshell can hold 10 electrons because d subshell has 5 orbitals. So after this, we have 30 electrons filled. Okay, after 3d is 4p, again 4p6. Okay, after 4p6 is 4d. Okay, is after 4p6 is 5s2 and 4d10, and then 5p6 and 6s2. Okay, after 3p is 4s. After 4p is 5s. Then 4d. After 4d, of course, is 5p. After 5p is 6s. Okay, 5p is 6s. So the electron configuration, I think that's 56. It's kind of 10, 20, 30, 40, 50, 56. Yes, those are the 56 elements. Okay, those are the electron configuration of these two. Again, practice in the order of the subshells, and also know each subshell can hold how many electrons. Okay, that's the electron configuration. And again, the electrons are in the order as the electrons are shown in these subshells as superscripts. Okay, don't forget that. Okay, now after we know that, I want to show you an even simpler way of doing the electron configuration. But before we do that, we'll have to take a look at a few examples, and then we take a look at the periodic again, so that you may understand a simpler way of filling in the electron configuration. Okay, if you look at the electron configuration of these 4 elements, okay, these 4 atoms, they're both from group 1A. They're alkaline metals: lithium, sodium, potassium, and rubium. Okay, I put the electron configuration here for you already. But if you notice that, all these 4 electrons of all these 4 electron configurations, they all end up with the same way. The same way means what? The electron arrangement in the outermost shell, in the highest energy. Okay, lithium, the highest energy is 2. Sodium, the high energy is 3, third shell. Potassium, high energy is 4. Rubium, the highest energy is 5. But the electron arrangement in the highest energy level is the same. Why is that? Because these 4 are in the same group. Lithium is 2s2 because lithium is the second period. Sodium is 2s1. It's lithium. Sodium is 3s1 because sodium is in the third period. Potassium is 4s1 because potassium is in the fourth period. And rubium is in the fifth period, so it is 5s1. But they all have one single electron in the highest level shell. They're all s1. Okay, that's one. So now you have a first impression. We're going to discuss more again. For impression that elements that are in the same group, and of course we talk about the elements in the same group will have similar properties. The reason is these elements have similar electron configurations. The reason the chemical properties repeat themselves in the periodic table, remember they cycle because elements can fall in the same group. The reason they cycle is the electron configuration cyclize. The electron configuration repeat themselves. Elements in the same group will have the same electron configuration. Lithium S2, sodium S2, potassium S2, rubium S2, S1, I'm sorry, S1, 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 S1. And the difference, of course, the highest shell is different. Lithium highest shell is 2, potassium highest shell is 4, rubium highest shell is 5 because they're equal to the period. But the electron configuration S1 are the same for these elements. The reason is the periodic table cyclize, repeat, because the electron configuration repeat. So that elements with the same electron configuration fall in the same group of their highest shell. Okay, of the electron configuration, I should be more accurate. Electron configuration of the highest shell, of the outermost shell, is the same for elements in the same group. If you understand that, you can take a look at the periodic table, and you have a better idea or a simpler method of drawing the electron configuration. You can see that we know this group is S1, right? First group is S1. Of course, period determines which S1, through S1, 3S1, 4S1. So if you move across the periodic table, you will find out S1 will become S2. And then after S2, there's empty. So this one will be P1, P2, P3, P4, P5, P6. Then it goes to what? 4S. Is that right? And after 4S, you have 4S1, 4S2. Then after 4S2, you don't have empty space. Now you have what? You have 3D. So 3D 1 through 3, 4, all the way to 3D 10. Then after 3D 10 will be 4P, 4P1, 4P, all the way to 4P6. Then the cyclize become 5S1 again. So using the periodic table as a guide, you can actually write the configuration a lot easier. Okay, for example, let me erase that. Let's try these two again, sulfur and barium, with the help of the periodic table. First, where's sulfur? Sulfur is here. So we know sulfur is here. If we write the periodic table, the electron configuration, we can just, from the first period, 1s2, 2s2, and then move on to the second period, that after 1s2, 2s2, and then we move on after 2s2, we got what? 2p, right? So 2p6. Okay, 2p6. And after 2p6, 1, 2, 3, 4, 5, 6, we get what? After 2p6, we get what? 3s. So 3s2. And then after 3s2, I move to 3p. Now, sulfur is here. This is 3p1, 3p2, 3p3, and what? 3p4. So sulfur is at 3p4. You can just move across the periodic table and find out the electron configuration. Okay, the same. Okay, same. Let's do barium. Okay, it's very low in the periodic table, but the same idea. Okay, 1s2, then followed by 2s, 2s2, and then 2p6 because it's 2p6, and then 3s2. After 3s2 is what? 3p6. After 3p6 is 4s2. And after 4s2, you got what? 3d10. After 3d10, we got 4p6. And after 4p6, I got 5s2. And after 5s2, I get 4d10. You can see I'm moving across the periodic table. 4d10. After 4d10, I get 5p6. Okay, 5p6. After 5p6, I move to what? 6s2, because that's the second one, 6s2. See that? I'm moving across the periodic table. I can fill in instructions, electron configuration with the help of the periodic table. Okay, again, this is another method to fill in the electron configurations using the help of the periodic table. Okay, again, I hope you to practice, find more elements, and just practice using your exercise from your book and also from a lecture. And after that, you will find out the electrons, again, they cyclize. So this periodic table will actually show you what is the electron configuration of these, all of these elements. Of course, we're not showing all the electrons, we're showing the electrons in the highest shell. Okay, because the highest shell electrons cyclize. So you can see that these are S1, these are S2, these are P1, P2, P3, P4, P5, P6. And these are all end with D, these are all end with F. So because of the electrons are filled, we actually divided our periodic table into 4 blocks. And these 4 blocks are different because each block shows you where the last electron is filled. If the last electron is filled in S, we call the block S block. If the last electron is filled in P, we call this pink block P block element. If the last electron falls into D, we call those D block element, which are transition metals. If the last electron is filled in F, we call those F block element, which are inner transition metals. See that? Okay, the periodic table is the cyclization of what? Of the electrons filling. Okay, cyclization of electron filling. Okay, and after that, there are 3 very simple practice. I hope you do use it and practice. Again, the keys are always provided in the note area. You can use that and as a practice, as an initial concept check to show you understand the concept chapter. Okay, I don't want to drag the lecture too long. So hopefully you understand, especially the second half is sometimes very abstract. You know the concept of shell, subshell, and orbitals. Okay, use this as a guideline. And also each subshell has how many orbitals, each orbital can accommodate how many electrons, and then try to fill in electrons in the order of increasing energy. And also remember, electrons in the same orbital must be opposite spin. If you have the energy of this, if you have empty orbital of the same subshell available, electron will first fill in singly with parallel spin, with the same spin first, before they pair with each other. So these are some extra rules when you fill. But again, practice with the filling. I think that's all for chapter 3. I'll see you in chapter 4. Bye now.